Okay, we'll get started. In this section, we're going to be looking at waves. So what is a wave, and then also the parts of a wave. So first thing, what are waves? Waves are disturbances in a material that transport energy, but they don't transport matter. For example, vibrations, sound, light, those are all examples of waves. So if you were to, let's say when you talk, what's happening is your vocal cords are actually making a disturbance in the air, and that disturbance is moving energy through the air, but it's not really causing air molecules from your mouth to move. It's and that's basically what sound is. So again, it's a disturbance in the air, and it's moving energy through that air, and someone else can actually hear that energy and interpret it as sound as you speaking. So again, that's what a wave is. It's a motion of energy. It's a particular motion of energy, but not the transfer of matter. So waves are an example of cyclical motion. And how are they an example? The way to think about it would be to look at, if you looked at an individual air molecule, for this example with sound, if you looked very closely at it, you'd see that it was vibrating. That even though the molecule isn't moving, out of your mouth to the person listening to it, if you were to look at it, it's vibrating back and forth very rapidly. So again, and that's doing it in a very specific, repeated way. So that's why waves are an example of cyclical motion, because even though all the parts aren't moving, there's individual molecules that are going back, forth, in a regular, repeated way. So that's why waves are cyclical motion. And waves, we can represent them. So again, it's a little hard to visualize waves, but they can be represented by a sine function. So this down here. So again, the sine function. And this is mathematically how we can think of waves, because the sine function actually goes up, down, up, down, up, down. It repeats itself. It's mathematically a way we can kind of analyze waves. So let's look at the parts of a wave. So the crests of a wave are the high points. So this would be a crest. This would be a crest over here. I'm just gonna write C for crest. And then there's the next part, troughs. Those are the low points in the wave. This would be a trough. This would be a trough. Write T. The next part, amplitude, is the vertical distance from the midpoint to the crest or trough. So the amplitude. So again, if this is the midpoint line right here, the amplitude would be right here. That would be the amplitude, or you could say it's the same amount for either, but from the midpoint to the peak, the trough, these would all be the amplitude, A. And wavelength, that would be the distance from between two crests or two troughs or any other identical adjacent points. So for example, if we look from this crest to this crest, the two successive crests, go from here to here, that would be an example of wavelength. It would also be an example if you went from trough to trough. That would be an example of wavelength. So it's basically how long the wave is. You can kind of think of it like that. That's wavelength. And then there's another quantity. So we're not really going to draw this on the sine wave, but wave speed. So that's how fast that wave is moving through a material. And the symbol for that is V. Oh, almost forget. So back with wavelength, the symbol's lambda. With A, it's amplitude. That's pretty straightforward. But with wavelength, it's lambda. That's this Greek symbol right here. So that's what it is. So wave speed, V, that's how fast it moves through a material. So again, sound's going to move a lot slower than light, for example. They have different wave speeds. And those, the frequency, so again, frequency from the previous section, wavelength, and wave speed can all be related by the following equation right here. So the wave speed is equal to the frequency. So frequency, how many times per second you see that wave, and the wavelength, so kind of how spaced out that the parts of the wave are. So again, this equation is going to relate these quantities. So that's it for this section, this 8b section. So waves, again, disturbances in material. There's different parts to the wave, and then you can relate two of those parts, or three of those parts, mathematically with the wave equation. Okay, so we'll move on to 8c. So 8c is going to be types of waves. Here you go. 8c. So 8c is going to be looking at, you have some idea what a wave is. Now we're going to talk about what types of waves are there. So one type of wave is there's transverse waves, where the particles are moving perpendicular to the direction the wave's moving. So what does that mean? Let's look at this example down here. If you had a slinky and then you move the slinky up and down with your hand, what's happening is energy is really being transferred from your hand into the wall, basically, right? That's the way the wave is moving. But what's happening if you look at it, individual parts, is this part's moving up, this part's moving down, this part's moving up, this part's moving down. So again, that's a transverse wave, where the wave is moving kind of up, down, but the energy is being transferred in the kind of the left-right direction. That'd be a transverse wave. Another type of wave is a longitudinal wave, so where the particles are moving parallel to the direction that the waves are moving. So this would be an example of a longitudinal wave right here. This is a transverse, right? This is the same picture, but this is a longitudinal wave right here. So longitudinal waves have compressions and rarefactions instead of crests and troughs. So again, this transverse had peak, crest, trough, crest, trough. This has compressions, so areas where it's bunched up. So like right, if you were to push the slinky back and forth like this, you'd get areas that are bunched up. The slinky's bunched up right here, right here. So this would be a compression, this would be a compression. And then you have rarefactions, so where it's less dense, where it's kind of split up. So right here, rarefaction. Right here, where it's less dense, where it's less bunched up. And it's that motion that's actually causing energy to be transferred. So longitudinal, you're still pushing energy kind of into the wall. You're transferring energy this way, the wave's moving this way, but the compressions and rarefactions are moving in that same direction as well. So that's a longitudinal wave. And the last kind of two types to look at would be mechanical waves. So mechanical waves are something that need a medium to move through. So sound, seismic. So again, that's a mechanical wave. If you don't have a medium, these can't move. The other type is going to be electromagnetic waves. So they do not need a medium to move through, or they don't need a material to go through. Light, radio, X-rays, UV, IR, infrared. So again, those are type of waves that do not need a medium to move through. So light will move through space, radio waves move through space, basically anything. They don't need anything to go through. Okay, so that's the 8B, 8C notes. And we're going to see a quick problem with this. Here we go. So make sure you attempt it before I go through it. Okay, we'll get started. So this says the string of a guitar vibrates back and forth, producing a sound wave with a frequency of 100 Hertz. Sound wave moves through the air at 340 meters a second. A is this mechanical, electromagnetic. Sound is a mechanical wave, meaning it needs something to move through. Air, water, concrete, something. So sound's a mechanical wave. B, what's the wavelength of this wave? So we know the frequency and we know the speed. If we want the wavelength, we could just plug it into the equation that relates to 3. We know the velocity, well, sorry, technically the speed, 340 meters a second. The frequency is 100 hertz. Get the wavelength. If we calculate, we're going to get the wavelength to be 3.4 meters. And the last part, what is the distance between two crests on a adjacent crests on a sound wave? So I mean two crests that are like right next to each other. That's going to be 3.4 meters because that's the definition of a wavelength. Basically, it's the distance. It's basically how long before the wave repeats itself. How long before you get another crest? How long before you get another trough? So that's the idea with this problem. It's just asking basic stuff about sound. What's its property, or what type of wave is it? You know, what are its properties? So make sure you have this. Make sure you have the notes all down, and that's it for now.